Hello and welcome everyone. My name is Samuel. I'm from Wells Fargo. Today I'm thrilled to present to you my latest research on the topic called asynchronous training of content reinforcement learning. In this presentation, I will cover the following topics. First, I will give a brief overview of quantum computing and its applications in the machine learning. Then I will give you the motivation for asynchronous content reinforcement learning. Then I will provide the basic concept of the reinforcement learning, and then I will introduce what is the asynchronous training of reinforcement learning agents. In the next section, I will further extend this asynchronous training framework to the content reinforcement learning field. So the idea is to combine asynchronous training with variational content circuits agents. I will also introduce the basic building block called variational content circuits. I will describe the numerical simulations and the results. Finally, I will provide a summary and key takeaways. The achievements of AlphaGo in 2016 drew a significant attention to the development of artificial intelligence and machine learning techniques. One of the critical parts in the success of AlphaGo is the deep reinforcement learning. Meanwhile, the development in quantum computing hardware is also significant. Since 2016, IBM provides cloud-based access to real quantum computers. And today, many big companies and startups are working on delivering larger and larger scale quantum computers. For example, IBM announced 433 qubit machine last November. With the great achievements in both reinforcement and quantum computing hardware, we may ask, can we merge these two fascinating technologies? For example, a reinforcement running on a quantum computer, or using reinforcement to further improve quantum computers. Among various proposals, variational quantum circuit is the leading method to build quantum machine learning, including quantum reinforcement learning. However, existing VQC-based quantum reinforcement learning suffers from long training time because computational resources are not fully utilized. So we may ask, can we further improve the efficiency of training a QRL agents? There are three categories of machine learning. Supervised learning is a type of machine learning where the algorithm is trained on a labeled dataset. The goal of the algorithm is to learn a mapping between inputs and outputs that can be used to predict the output for new unseen inputs. For example, in image classification, a supervised learning algorithm is trained on a labeled dataset of images and their corresponding labels. Unsupervised learning, on the other hand, is a type of machine learning where the algorithm is not given labeled data. The goal of the algorithm is to find patterns or structure in the data. For example, in clustering, an unsupervised learning algorithm groups similar data points together. In reinforcement learning, the algorithm learns by interacting with an environment and receiving feedback in the form of rewards or penalties. RL is a type of machine learning that is based on learning from experience, while supervised and unsupervised learning are based on learning from labeled or unlabeled data. RL is a type of machine learning that enables an agent to learn by interacting with an environment. The environment consists of a set of states, actions, and transition probabilities. At each time step, The agent observes the current state of the environment and selects an action to perform based on its policy. The environment can then transition to a new state and provides the agent with a reward signal that reflects the quality of the action taken. The agent's goal is to learn a policy that maximizes the cumulative reward over time. The RL agent itself can be a deep neural network or a variational content circuit. The asynchronous training framework is a special kind of reinforcement training method that multiple concurrent actors can learn the policy through parallelization. As shown in this figure, many parallel executing agents can run in parallel with multiple instances of the environments. These methods allow the agents to encounter diverse states and on policy reinforcement such as the actor-critic, which is the method we used in this work. Another feature of the asynchronous training framework is that there is no need of replay memory. In the asynchronous training framework, we will have a global parameter and several local workers. Each of the local workers will play with its own environment and calculate its model gradients, and then share the gradients with the global parameter. The global parameter will be updated accordingly, and then the local worker will copy the updated global parameter to do its inference in the next time step. The asynchronous means that we don't need to wait all the local workers to finish. When each of the local worker finish its part, it can just upload its gradient and get the global parameter updated. So it is much more efficient in this way than waiting all the local workers finish their episodes. In the asynchronous training of quantum reinforcement, we use the variational quantum circuit as our agent. The variational quantum circuit is a kind of quantum circuit with tunable parameters. And these parameters can be updated or optimized using gradient or gradient-free method developed in the classical machine learning. There are three critical components in the variational quantum circuit. The first is the encoding circuit, U of X, which is to encode the classical values into a quantum state. And the variational quantum circuit, the V of theta, which is the actual learnable part, and the final measurement, which we can extract the information from the quantum circuit. The hybrid quantum classical paradigm used in this work is suitable for currently available NISQ devices. The idea is that certain parts of the calculation are performed on the quantum computer, while the optimization procedure is carried out on the classical computer. With this framework, we can easily apply the optimization method developed in the classical machine learning community. The variational quantum circuit can be incorporated with other classical components, and the whole model can then be optimized in an end-to-end manner. The gradient calculation of quantum circuits follow the parameter shift rule. It means that for calculation of a gradient with respect to a single parameter, 2 circuit rounds are required. This method is different from the finite difference method since it does not have the infinitesimal part. Therefore, parameter shift rule is more numerically stable. The VQC used in this work is called dressed VQC. We employed the classical deep neural network before and after the VQC to dimensionally reduce the data and fine-tune the outputs from the VQC respectively. The neural network components in this hybrid architecture consist of single-layer neural networks for dimensionally conversion. Specifically, the neural network preceding the VQC is a linear layer with an input dimension equal to the size of the observation vector and an output dimension equal to the number of qubits of the VQC. The neural networks following the VQC are linear layers with input dimensions equal to the number of qubits in the VQC and output dimension equal to the number of actions when we consider the actor function pi, or 1 if we consider the critic function v. These layers serve to convert the output of the VQC for use in the actor-critic algorithm. We consider 3 simulation environments. The first one is the coupled environment, which is a very standard RL environment in the OpenAI Gym. There are 4-dimensional vectors comprising values of car position, car velocity, pole angles, and pole velocity at the top. And there are 2 actions there, push to the left or push to the right. A reward 1 plus 1 is given for every time step where the pole too close to being upright. The acrobat environment includes 6-dimensional vector observation and 3 actions. For the reward, an action resulting in the free and reaching the target height receives a reward of 0 and terminates the episode. Any action that does not lead to the desired height receives a reward of -1. We also consider 3 mini-grid environments. The observation is a 147-dimensional vector. There are 6 actions in this environment, and the agent will receive a reward of +1 when reaching the goal. A penalty is subtracted from this reward based on this formula. We consider the quantum and the classical models with similar number of parameters to compare their performance. We begin by evaluating the performance of our models on the acrobat environment. The total number of episodes was 100,000. As shown in the figure, the quantum model exhibits a gradual improvement during the early training episodes, where the classical model struggles to improve its policy. In terms of the average score, the quantum model demonstrates a superior performance compared to the classical model. In addition, the quantum model exhibits a more stable convergence pattern. For the coupled environment, we also observe that the quantum model can achieve a much higher score than the classical counterpart. The final experiment was conducted in the mini-grid environment. We can observe that 2 of the 3 cases we tested, the quantum model can beat the classical model with similar architecture and a number of parameters. The other one, although the quantum model is not as good as the classical model, the difference is minor. In conclusion, The asynchronous training of quantum RL can be used to improve the training efficiency of QRL. When the number of parameters and architecture are similar, quantum version models can outperform classical models. The training of quantum reinforcement agents through parallelization may have potential applications in various real-world scenarios. Thank you. Thank you for your listening.